أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم قل هو الله أحد الله الصمد لم يلد ولم يولد ولم يكن له كفوا أحد صدق الله العظيم. On behalf of the Comstech and IEEE Karachi section educational activities, we welcome you all, the participant in 2 days workshop on contextual probability concept, implementation and application, 26th and 27th October. So that a joint program organized by Comstech, Ministerial Standing Committee for Scientific and Technological Cooperation in collaboration with IEEE Educational Activities, Karachi section. So contextual probability is a method of non-programmatic probability estimation without using any model assumption there. So we are very much thankful to our resource person, Professor Hui Wang. He obtained his BSc in Computer Science and MSc in Artificial Intelligence from Jilin University, China, and his PhD in AI from University of Ulster, UK. He is currently Professor of Computer Science. His research interests are knowledge representation, reasoning, learning, and enumerative combination and application in multi-video search and search data analytics. For especially, he worked about food authentication and virus detection there. And during the COVID, I lots of time talked to the Professor Hui Wang, and he's busy in such projects related to this pandemic situation there. He has over 270 publication in these areas, and lots of his research productive and contribution toward the scientific application there. It's a great honor that we have with us the Professor Dr. Muhammad Iqbal Chaudhry, Coordinator General Comstech. He is a very noble and renowned scientist and the pride of our country, Pakistan. We love you all, sir, and thanks for your time to be here. Dr. Saab have over 1,200 publications in the field of organic and bioorganic chemistry, including 40 US patents, 76 books, and 40 chapters in books published by major US and European press. He has more than 27,000 citations and having an H index of 68. 94 scholars have been awarded PhD under Dr. Saab's supervision. Dr. Saab has awarded Civil Award Hilal-e-Imtiaz by the President of Pakistan in 2007. He is also awarded Civil Award Sitare-e-Imtiaz in 2001, and he has also awarded Tamga-e-Imtiaz in 1999 by President of Pakistan. So he has a more list of awarded and contribution towards this nation, towards this country, and our University of Karachi there. And I'm really thankful to sir to be here, to be a part of this program, a 2-day handout. And Dr. Saab is always encouraging such kind of academic activities, and he also insisting to be a part of such kind of activities in coming future as well. So I request Professor Dr. Iqbal Chaudhry for welcome address, please.
My dear Professor Hui Wang, my dear Professor Dr. Sadiq, Dr. Hina Siddiqui, Khazima Muazzam, other distinguished colleagues and scholars, I would like to welcome you on behalf of Comstech, which is a ministerial standing committee for all Muslim countries, 57 of them. And as Dr. Sadiq mentioned, that the primary objective of Comstech is to promote science and technology. And this is extremely important, that the benefit of science and technology is spread far and wide. Because so far, largely, except a few, science and technology has been used as a tool for making profit by large companies. But I think it's a time for us to redefine why science and technology is important and why it needs to spread to every part of the world where people need it the most. So primary objective of comstech is to promote science and technology for the common human well-being and benefit. And we have with us an extremely distinguished colleague. I'm absolutely impressed from reading his biodata, which spread from uh, his intellectual depth of coining a new terminology and initiating a new field of contextual uh, probability, and then taking it to the next level. So as Dr. Sadiq mentioned, this is exactly what we need. Such people are great source of inspiration and knowledge. And we are so fortunate to welcome Professor Wang today in this 2 days workshop and hands-on training initiative. With this, I would like to request Professor Wang for his lecture.
Okay, thank you for the invitation and for hosting this this workshop. And it is a great honor to have the opportunity to speak on this forum. Okay, and thank you to Dr. Sadiq for the kind invitation and for the introduction. And okay, I think I need to share my screen.
Yes, please.
And okay. Can you see my screen now?
We can see.
Okay. Okay, good morning, and should be good afternoon in your place. Good morning, everybody.
Good morning to you.
Okay, and this is the title of my talk, and so I'm going to talk about contextual probability and neighborhood counting. So this is the outline of my talk. So I have a list of 6 bullet points to cover. And so this talk focus on contextual probability. And so that is a kind of probability estimation methodology. And then I will cover I will talk about neighborhood counting that comes from the contextual probability. And if you want to estimate the contextual probability, then you need to go through neighborhood counting. And neighborhood counting turns out to be a similarity kernel. So that is not just the counting method, it is actually a generic similarity measure. It has some very nice properties. And then it is generic. So if you want to use the similarity kernel, you have to specialize the similarity for a specific form of data. And the data can be multivariate. And then the neighborhood counting becomes the NCM. And we can also specialize the similarity kernel for sequence data and resulting in the ACS. We can also specialize the generic similarity measure for graph data, and that results in the path kernel. So that is the outline of my lecture. And I use the Beamer, the LaTeX Beamer to generate this presentation, and I use the theme bar at the top. So at any slides, you should be able to see 2 theme bars. So on the left-hand side, that is the main list of topics I'm going to talk. And on the right side, so you will see a list of subtopic. So under each main theme. So at any one slide, you should be able to know precisely where the slides is actually about. So you will not lose the context of any particular slides. So this is the outline of my lecture. Now going into the contextual probability. Okay. Okay, so this is, let me see. Yeah. And so I hope by the end of the workshop, and you should have opportunity to learn a new methodology for probability estimation. So if you have experience in probability estimation, then this is a different methodology for doing so. And also, you have the opportunity to learn the methodology for similarity measurement. And also you have opportunity to appreciate the power of dynamic programming and matrix operation as well. And finally, so this is an opportunity to see, to witness a journey from its conception to its fruition. So that is what I hope to achieve by the end of this workshop. Now coming to the first topic of this workshop, so contextual probability. So I divided into 5 parts. So I'm going to talk about the motivation, the concepts, the properties, and I'm going to show some examples. And above all, I want to highlight the value of the contextual probability. Now, for anything you do, and especially in the scientific field, so you must have a motivation. Then the motivation for contextual probability is probability estimation. So when I started working on this, I wanted to estimate probability, but I realized there is some issues, and in some cases there are some difficulties in doing so. And we know the probability distribution is very important, and in many problems areas. So if we know the probability distribution over a data space, then the problems can be solved quite easily. But the question is, in practice, the distribution is not known. So if you want to use the probability tool to solve the problem, so you have to find a way to estimate the probability in one way or another. So the probability estimation is not new. It is not new, and there are many probability estimation methods. And so it can be non-parametric methods. And if you take this route, you need a lot of data. And if you don't have a lot of data, then your estimation may not be so useful. And the estimation method can be parametric methods, where you have a specific form for your probability distribution. And one example is the Gaussian distribution. So you assume that your probability distribution is Gaussian, and then you only need to estimate the parameters. But the problem with the parametric method is, and if the real distribution is not what you're supposed to be, then you are biased. So that is a problem with parametric methods. And then there's the Bayesian method. The Bayesian method is break down the Bayesian theorem into the simpler forms, so that you can estimate the probability distribution through the simpler quantity estimation. But this approach is exponential by its nature. And so if you want to do so, you really need to have the background knowledge to constrain your search space. So background knowledge is typically needed in order to reduce the complexity of your estimation. So another approach is the naive Bayes. And so once again, this is based on Bayesian theorem, but it assumes conditional independence between the variables. In some cases, this assumption is true, but in many situations, this independence assumption is not true. So there are problems with existing method. Okay, and let's take a simple example. Now, suppose we carry out an experiment, the coin tossing experiments, and we know the results. The result sets are the head and tail. So that is all possible outcome of the coin tossing. Now, if you repeat this experiment 8 times, then you see the results like this: the head, and tail, head. Then you ask the question, then what is the probability of the head showing up next time you toss a coin? Then what is the probability of tail? Then to answer this question, you can calculate the frequency of head or tail in your data set, in your experiment result set. Once you have the frequency, then you should have a good idea of the probability of head and the probability of tail. And if you continue this experiment until infinity, then you will arrive at the true probability of head or tail. So that is actually the classical definition of probability, which is the limit of frequency. So for this problem, the probability estimation is simple. But what about the next one? And in this example, the experiment centers around the grid, and every grid corresponds to a 2-dimensional data tuple. Assuming that we have already seen the results, 5 results. So those cells, this cell. So these are the known cells. Then I ask you the question: and what is the probability of next experiment landing in this cell? And further still, what is the probability of the next experiment coming up as a plus, as a plus sign? Or what is the probability of the next experiment landing here and as a minus? So assuming that you are supposed to estimate these probability quantities, then if you take the same approach, which is the frequency-based approach, then there is a problem. You want to find out the frequency of the result landing here, but before this point, there's no data points in this cell. So you will get the value of 0 in many places, but you still want to know the probability of the result landing in that cell. Then the frequency-based approach will run into problem, and you really need to have a huge amount of data that covers most of the space, most of the cells in this space, before you can actually take this approach to estimating probability. And okay, then we know that there are problems, and my motivation and my approach is like this. So my strategy to solve this problem is assuming that we want to estimate a probability distribution for a specific problem. So there must be a probability distribution there, but I don't know what it is. And I know it is difficult to estimate that particular quantity. Then my strategy is I define an easy to estimate function that is related to the function that I am interested. And then I estimate the easy function instead. So once I can estimate the easier function, and then I can get hold of the probability quantity or the distribution that I want. So that is my strategy. Okay, so this strategy is based on my experience working with k-nearest neighbor. And we know the k-nearest neighbor classifier, that is simple, but it is still quite effective. It is still quite effective, and it is still widely used in practice. And so for any data points, and in order to classify the data points, we consider a number of nearest neighbors or k-nearest neighbors, and then we use these neighbors to estimate the class probability. So that means the data points belonging to certain class. So I estimate the probability of a data points belonging to a certain class. So that is how k-nearest neighbor works. And there are in fact many different ways of finding neighbors. And each way of finding neighbors results in a so-called neighborhood. So that is essentially a region around the data points. And if you have a different way of finding neighbors, then you end up with different neighborhoods, a different region around the data points. Now, the question is, if you consider not just one neighborhood, but you consider all possible neighborhoods, how do you combine these neighborhoods to estimate the class probability? And then this question leads to the notion of contextual probability. Now, before we look at the contextual probability, we need to know the classical definition of probability. So the classical probability has different interpretations. So this is the well-known interpretations. One is the frequentist. So as I explained earlier, for the frequentist approach to estimate probability, you need to begin with a sample, and then you calculate the frequency of the class, and then you can estimate the probability based on the frequency. And the other one is the Bayesian approach to probability estimation. In this case, you don't start with a sample, but you start with a prior, and then your knowledge is encoded in the prior rather than in the sample, and then you apply your knowledge, and then you can work out a probability distribution. But the mathematics underneath both approaches is the same. So we have a quantity, mathematical quantity. We have a set. So that could be the set of experimental results, like the head and tail in the coin tossing experiment. So the omega is a set, and then the F is a sigma algebra over omega. So the sigma algebra that is essentially a set of subset of omega, which is closed under intersection or under union, and importantly, it is also closed under complement. So that is the definition of the sigma algebra. So F is such a sigma algebra over omega. And one good example of the sigma algebra is the power set of omega. So that is one example. And then a probability function is defined in this way. So that is a mapping from the sigma algebra to the interval between 0 and 1. And such that the function must satisfy the axioms of probability. So that includes the non-negativity, meaning that the function value must be non-negative. And saturability axiom, meaning that the probability of the whole set, the probability of the omega, that should be 1. Should be 1. And the third axiom is the additivity. And this means that if you, and the probability of two disjoint set, you have one set, you have another set, they are disjoint, they have no overlap. Then the probability of these, the union of these two sets should equal to the probability of this set plus the probability of the other set. So that is the additivity, but the mathematical treatment would be more complex than this. So actually any function that satisfies these three axioms is actually a probability function. It is a function, but the meaning of the probability value you calculate in this way may not be the probability of in the frequentist sense. So therefore, we have a probability space that consists of a set and each sigma algebra plus the probability function. So that is the object of study for probability. And contextual probability is defined in this way. So we begin with a probability space. So that is, and so that means, so we have a probability that we are interested and we want to estimate this function. But instead of doing so directly, we define a new function like this. And so new function G maps the f to the interval as well, such that for every element in f, we define the G value in this way. So this definition means that we need to go through every element in f, and then we calculate the probability value for this element, and then we weight this value by the f value, but it is the f applied to this x intersection with this e. So we look at the intersection of the two sets, and then we calculate about the f value. And the f value, it is a measure. It is a measure of the set. So the fx is a measure of set. And one example is so this function is simply the cardinality of the set x. So that is one concrete example. And the k is a normalization factor. So this is the definition of the contextual probability. So it looks quite complicated because if you want to calculate the G value for X, you need to go through every element in this set. So that seems quite complicated. And it turns out this G function is a probability function because it satisfies the three probability axioms. And then I call it contextual probability. So this one was, let me see this. Yeah. So the contextual probability was first published in 2003 in this journal. But then later on, I had some subsequent research which were published in different places. So I call it the contextual probability. And the reason I call it contextual probability is because in order to estimate this probability, you need to go through every element in the F, and every E is a neighborhood. So that would be a context. And you consider all the possible contexts to estimate the probability. And so that is the origin of this term, the contextual. So we take every E as a context, but you consider all possible contexts. And the given probability P is the primary because that is what you are interested. And then as a means to estimate the P, which is G, is called the secondary probability. So that is the means to estimate your P probability. And so the elements in the omega are individuals. So we can see the elements of the omega as individuals in the space. You can imagine in the data space. So and there are points and there are regions. So the points are the elements in your data sets. And then the regions satisfying certain conditions would become the elements in the F. And then the regions in the space satisfying those conditions are called the neighborhoods. So that is the definition of contextual probability. Now, there are some nice properties of the contextual probability. So as I mentioned earlier, contextual probability looks quite complicated because you need to go through all the elements in the F to calculate a single value. So that is the mathematical definition, or that is the meaning of this function. But actually, so this probability has a simple relationship, linear relationship with the primary probability. So that is the result of this theorem. So the contextual probability of any element can be calculated, is related to the primary probability of the same elements weighted by a quantity alpha, and the alpha is like this. So that is 1 over n plus 1, and n is the number of elements in the set omega. So that is the cardinality of the set. So we assume the set is finite for the two quantities to be linearly related. So there is an open question, which is the relationship between the two quantities when the set is infinite. But I haven't I haven't found a solution to this question yet. And another theorem is like this. So that means, this means that still you have the primary and you have the secondary, and you consider their conditional probability of a class of classes. Then given any data points in the data space, and then so their relative relationship according to the primary is identical to the relationship between the two quantities according to the secondary. So this relationship is equivalent to this relationship. Meaning that the primary and the secondary, they maintain so this inequality relationship. And the implication of this equivalence is, and the primary and the secondary, they are equivalent in classification. So if you use the Bayesian optimal classifier, and then the G and P should give you identical result. So they are equivalent. So these are the theoretical properties of contextual probability. Now, so I mentioned earlier that the motivation of this work is probability estimation. So we have defined a secondary function in terms of the primary. And to estimate the primary, I go through the secondary. So I have to estimate the secondary in the first place before I can find the value for the primary. So I need to estimate the contextual probability in the first place. Now, how to do so? And there is a theorem. There is a theorem which tells us how to estimate the contextual probability. So this means that given the data sets, so that is the sample, for example, the set of experiment result that we saw earlier. And then for any data instance in the data space, its G value is actually proportional to this quantity. So this quantity means that we need to consider all the data points in the data space. And then we calculate the C value. We calculate the C value. And the C value is defined in this way. So it considers every element in the F, which is the sigma algebra over data sets. It considers every element in this F. And then we must make sure that both T and X is a member of this E. So E can be thought of as the region. And then this region should contain both T and X. So the meaning of this quantity is the number of the all common neighborhoods of T and X. So that is the meaning of this quantity. So if you can calculate this quantity for all the instances in your data set, and you put them together, then you normalize it to become a probability value, then that gives you the G value. So this means that the G value can be estimated in this way. And actually the quantity C gives rise to a similarity measure, and I call it neighborhood counting similarity. So this will be discussed in the second topic of this workshop. Now let's take a look at the example we have seen earlier. So that is again the coin tossing. So we have the data space, and then we have the sigma algebra, which is the power set, and we have the experimental result, that is the data set. And in order to estimate the quantity, the probability of H and the probability of T, we can calculate the frequency directly and then to estimate the p-values. But now we have an alternative way of doing so. So we can estimate the G value in the first place, and then we can work out the p-values through that simple linear relationship. And in this case, the data space is finite. We have only two values. So the p can be easily worked out from the G values. And so I leave this one as an exercise. Okay, now for this experiment, we know that using the frequentist approach to estimate the p-value is problematic because we don't have a lot of data. But then we can estimate the G probability quite easily. Okay, and let me have a little pause. Let me close my email system because I sometimes receive email messages, so that we are not interrupted by this. Okay. So let's look at this one. Assuming that we want to estimate the probability, we want to know the probability of a next experiment landing in this cell. And we know that the frequentist approach to probability estimation is problematic, as we don't have a lot of data. Now, how to do it through contextual probability? So we need to know the data space and the sigma algebra. So the data space would be the set of all these cells. So we have 5 by 5 the grid. So we have 25 cells. So that is the data. That is the data set. Now, what about the sigma algebra? The sigma algebra would consist of the regions in this data space. So this is one region, and this is another region, and so every rectangular region is a neighborhood. So this is only one way of defining neighborhoods. There may be other way of defining neighborhoods. So one sigma algebra would consist of all possible rectangles, rectangular regions. So that is one specification of the sigma algebra. And another way of specifying the sigma algebra is we don't consider all possible the rectangular regions. We only consider certain. So that is possible. That is possible. But assuming that we consider all possible rectangular regions as the sigma algebra, and the estimating, for example, the g of t can be done in this way. So we assuming that we consider this rectangular region as one neighborhood. Okay. Okay, and in order to estimate the g of t, all we need to do is to calculate the similarity, that c value between t and this one, t and this cell, t and this cell, t and this cell, and this cell. So we only need to calculate 5 quantities. So which is the c value, and the c of t and this one, and the c of t and this one. And so that means, let's consider this one, t and this cell, and to calculate this quantity means we need to count the number of regions that cover both t and this plus, and that will include this one. This is one rectangle. This is one neighborhood, and this is another neighborhood, and this is another neighborhood, and this is another neighborhood, another neighborhood, and another neighborhood. So we have so many different neighborhoods. So again, that is still quite complicated to calculate that c value, which is the number of neighborhood covering the 2 data points. Now the question is there a simpler way of doing so? And the answer is yes, there are simpler ways to do so. But in order to know what is the way to do this counting, So we need to specify, we need to know what type of data we are working on. And for different types of data, you have different ways of calculating the C value. And if your data type is multivariate, then you can work out this number by a formula. But if your data type is sequence data, and then we have the dynamic programming algorithm to efficiently calculate this quantity, and so on. Now, so clearly, contextual probability has values. So its main value is, so it provides a new way of probability for probability estimation. So this method is non-parametric because we don't assume any specific form for the probability distribution. So that is non-parametric. And it has no independent assumption. We don't need this assumption for the method to work. And it is less bias because we don't use any parametric approach. And we don't need any background knowledge for the method to work. So so these are quite desirable, properties. And more importantly, so it gives rise to a generic similarity measure, as I mentioned earlier, which is the neighborhood counting measure. And so I have said that the contextual probability is a way of probability estimation. And historically and traditionally, there are some the well-known method for probability estimation. So one popular method is the Parzen window method. So the task is like this. And again, we are given the data, a sample of multivariate data, and we want to estimate the joint probability for a data instance in the multivariate data space. And this is estimated through this formula. So this formula means that the phi function is parameterized by the h, and the h is the length of a hypercube in the hyperdimensional space. And so that defines the width of the little window in the multidimensional space. And then you estimate the probability through this window. So for any data point, you use this window, and you use the data points within this window to estimate the density of x. And so h is the width of the window, and the v is the volume, and m is the number of data points. So that is the popular density estimation method. So the problem with the Parzen window is the width of the window, the best width of window is unknown. So that is a problem. That is a problem. And to see the impact of the window width, let's take a look at this one. So if the window width is too big, then you end up with an estimation like this, a density estimation like this. That is the big one. And you cannot capture the fine details. But if your window width is too small, then you end up with these spikes. So they are too detailed. And the appropriate one would be the green part. So it is difficult to find the optimal the width of the window. So that is a hyperparameter you need to estimate for your particular data set. And another popular method for probability estimation is the kernel method. And for the same task, we estimate the density through this formula. And the main elements of this formula is the K function, that is the kernel function. So this kernel function is bounded by with integral 1. So it still need to go through every data points in your sample, and then for any sample you calculate the value this quantity. So that is the kernel value between x, which is what you want to estimate for, and one data instance in your sample. And then you calculate the kernel value. You put them together, and then you normalize it by the m. That will give you a probability estimation for data point x. And the problem with the kernel method is the choice of the kernel is hard. And actually another problem is, and the actual meaning of this kernel is unclear. And if the kernel function is unclear in its meaning, then the probability value, the meaning is unclear as well. Even if you can have a probability value, so that satisfies the probability axioms, it may not be the quantity that you are expecting. And so there are other estimation methods. And so the direct method, which is what I call the non-parametric method. So that is frequency-based. So this is the frequency. But this method depends on the amount of data. You really need to have a lot of data before you can have a good estimate. And then the Bayesian, so you need to work according to the Bayesian theorem. So you need to break down this joint probability into conditional probabilities. You need to break this part further down. So that becomes exponential. And naive Bayes can break down this joint probability in this way. So that is because we assume conditional independence, but this assumption may not be valid. And there could be model-based approach to estimate probability. So we assume that, so this is the parametric approach. So we assume that the distribution takes certain form, and then all we need to do is to estimate the parameters of that function. And so these are the popular estimation methods. I wonder. Okay, before we move to the next topic, can we have a 5 minutes break? I would propose that we have a 5-minute break. So it is now 2 past 10 o'clock. Can we come back can we come back in 5 minutes? I would suggest we have 5-minute break, and then we will come back at 7 minutes past 10, which is my time here in Belfast. Okay, I want to add some more water. I want to Okay. Okay. Okay, so good afternoon again. So we are going to start looking at the second topic, which is the neighborhood counting as a generic similarity kernel. And so in this part, we are going to run through these headings and the motivation, the definition of the similarity, and then the definition, and then some properties. So I want to explain why it can be regarded as a similarity metric, why it is generic, and why it is a kernel function. Okay, and so the motivation is twofold. So first of all, it is inspired by the contextual probability estimation. So remember the theorem I showed earlier. And contextual probability can be estimated in this way, through this formula. And so there's the C function, and so that need to be calculated for all the data points, and then we put them together. So this is quite similar to the kernel method, but the C function has very specific meaning. So that means that is the number of all neighborhoods that cover both T and X. So compare this one to the kernel method we saw earlier. So this is quite comparable, but the C function has precise meaning. This is the physical meaning of this function. And so the neighborhood counting is inspired by this. So this is when I realized, when I was working on the G estimation, so I came to this point, and then I realized, so this C function actually is quite meaningful. Then I started to investigate precisely what it means, and then I realized that is actually quite a useful quantity. So another motivation is the desire for a general way of measuring similarity. So it is a general way of measuring similarity that can serve as the motivation for this work. So there are existing similarity measures, but they typically work for a specific type of data. For one example is the Euclidean distance. And this measure only works for multivariate data, and it doesn't work for the sequence data, and it doesn't work for tree or graph data. And then the question is, do we have a general measure that works for all types of data? So if we ask such a question, then that will motivate us to search for a general method. And it turns out the neighborhood counting is indeed a general method. Before we discuss whether neighborhood counting is a distance or similarity metric, we need to know precisely what is a distance metric. So a distance metric is a function like this, such that for any for any 3 elements we have these properties. So the first one is the non-negativity, and the second one, that is the identity of indiscernibles. So the distance is 0 even only if the 2 points are identical, and the d of x and y is the same as the d of y and x. That is a symmetry property, and importantly, this is a property, is an important property, and it is called the triangle inequality. So this triangle inequality is important in some specific applications. And you can exploit this triangle inequality. And for example, in information retrieval, and if you want to find the nearest neighbors, and one approach is you go through all the data points in your sample, and then you calculate its similarity or its distance. And so that is called the brute force approach. But you can exploit this triangle inequality in designing your search algorithm, so that once you don't have to go through all of these, you don't have to go through all pair of these. And so there are search algorithms which exploits this triangle inequality property. So if a function satisfies all conditions, and then it is called the distance metric. But if a function satisfies all conditions except triangle inequality, it is usually called the distance measure, but it is not necessarily a metric. So the distance metric has precise meaning. It must satisfy all these properties. And similarly, we have the similarity metric. So similarity metric is related to distance metric. So the similarity metric is a function like this, and such that it satisfies these properties. And once again, we have an inequality. This is an important inequality, which is similar to the triangle inequality. And we can exploit this inequality in designing certain algorithms to reduce the search space. But usually you don't need to bother the triangle inequality or the inequality here. So only if you want to do efficient search, only if that is the case, you can exploit this quality. So this inequality. And we can build a similarity metric from distance metric and vice versa. So this means that if you have a similarity metric, and then you can easily turn it into a distance metric. And vice versa, if you have a distance metric, you can easily turn it into a similarity metric. And so that is, and so and any function that satisfies these five the properties is a similarity metric. And it turns out the neighborhood counting is a similarity metric. And I will explain why it is the case later on. And there are many similarity or distance measures. So I call it the similarity or distance measures, because the similarity can be easily turned into a distance measure. So for example, the Haiming distance, the Euclidean distance. So these are the common ones, and less common ones include the Mahalanobis distance. So this distance is commonly used in statistics, and the value difference metric, and the minimum risk metric, and the eddy distance, and the maximal subgraphs. So these ones all work for the multivariate data, but the eddy distance, so this works on sequence. For example, the Levenstein eddy distance that works only on sequence. And so that it can be applied in coding theory, for example. And the maximal subgraph, the similarity measure, it works on graph, and it can find applications in graph theory. There's so many the similarity or distance measures, and each works for a specific type of data. So that motivated us to search for a general similarity measure which works on all types of data, at least at the conceptual level. And the neighborhood counting is indeed such a general similarity measure at the concept level. So the definition of this similarity measure is like this. So we begin with the data set, that is data space omega and the F, as we have seen before, and we define the function C like this, such that, and so the C value for two data instances is defined as the cardinality of this set. And so this, we have seen this before. That is actually the set, the number of all common neighborhoods of X and Y. And this function is a generic similarity kernel. So it is generic, it is similarity, and it is a kernel function. So why it is a similarity? Why it is a similarity measure? Because this, to qualify as a similarity measure, you need to satisfy two minimal conditions. So when the two objects or two data instances are they are identical, then their similarity should be maximal. But if the two objects are completely irrelevant, and then their similarity should become 0. So these are the two extremes, and the function should satisfy these two conditions to be called the similarity measure. So this is indeed the case for the neighborhood counting. And so when X and Y becomes identical, they become the same the same data points in the space, then the C value will become the number of all neighborhoods in the neighborhood space. So that becomes the maximum. And when X and Y, so they are quite distinct, then they have less, so they have minimum number of neighborhoods to cover both of them. So when X and Y becomes quite distinct, then they have nothing in common. So there's no neighborhood that covers X and Y, both X and Y, except the omega itself, that is the whole set. So that is the only neighborhood that cover both X and Y, if X and Y are the most distinct. So the C function satisfies these two conditions. So it is a similarity measure. But it is also it also satisfies the similarity axioms. So I showed you the axioms before, the 5 axioms for similarity metric. It also satisfies those axioms. So it is complicated to prove one property, and so I probably will skip this. So it is a kernel function. So it is a kernel function because it satisfies the one key property of the kernel function, which is the C value can be broken down into the product of 2 additional quantities. So I'm going to show you this point at a later stage. And why it is generic? And this is because the C is valid. So the concept is applicable to all forms of data because we can talk about the neighborhood for all forms of data. So in the case of multivariate data, the neighborhoods can be rectangles or the hyperrectangle in multidimensional space. And I'm going to show you what a neighborhood is for sequences. I will also show you what the neighborhood is for graphs. So we can talk about neighborhoods for all forms of data. So the neighborhood counting similarity is applicable to all forms of data at the concept level. So the neighborhood counting similarity concept was introduced in this paper. And so this paper, that is, yeah, so that is published in this paper. So this is not the first time neighborhood counting similarity was introduced, but this paper discussed this similarity in great detail. And in order to calculate the neighborhood counting similarity, all we need to do is to count all common neighborhoods. But how to do so? That is a question that we haven't answered as yet, but we will do so later on. Now here is an intuitive interpretation of the neighborhood counting similarity. And here we have points and we have regions and we have the data space. So this is a 2-dimensional data space. And the circles are regions, and they can be regarded as the neighborhoods. And then we have points which are labeled by T, A, and B. So we can take every, we have points and regions, or the data points and neighborhoods as well. Now, if we want to if we want to calculate the similarity between T and A, and according to neighborhood counting, and all we need to do is to count how many neighborhoods that covers both T and A. And in this case, assuming that the circles are all the neighborhoods that we consider, then how many circles that cover both A and T? We have 1, 2, 3, 4, 5. So we have 5 circles that covers A and T. And then the NCM becomes 5. Now we want to also measure the similarity between T and B. Then all we need to do is to count how many circles that cover both B and T. And in this case, we have 2 circles that cover both B and T. And as a result, we can see that the A is more similar to T than B, because the similarity between A and T is 5, but the similarity between B and T is 2. So on the basis of that, we can conclude that A is more similar. So that is an intuitive interpretation. But your neighborhoods, the neighborhoods may not be the circles. The neighborhood can be rectangles if your space is multidimensional. It can even be of other forms. So there would be different ways of defining neighborhoods. It all depends on your problem at hand. And I'm going to show you different forms of neighborhood for different types of data. And so the neighborhood counting is a similarity metric. It satisfies the five axioms of similarity metric. So this is the symmetric, and this is non-negativity, and this one, and this inequality, and this one as well. So I will leave the verification as an exercise. And the NCS is also a kernel. It is also a kernel. And the kernel function is defined in this way. So a kernel function should satisfy this. And so the function value can be calculated as the product of 2 vectors. So if a function can be calculated in this way, then it satisfies the basic requirement of a kernel function. And it turns out the NCS, the C function can be calculated in this way. So that is the inner product of 2 vectors. So the phi of x, so that is a binary vector in the space spanned by all the neighborhoods. So you imagine you have the neighborhood space. So you have a set of neighborhoods. So you arrange these neighborhoods. You put the neighborhood one after another. So you need to make sure the neighborhoods are countable. Then you can put these neighborhoods the one after another. And then, so you can say that this neighborhood is in the first position and that neighborhood is in the second position. So if you can do it in this way, then you can construct a vector. You can construct a vector for any the data instance. And so in this vector, if the vector has a value of 1, that means value of 1 for one position. That means, and so the neighborhood corresponding to that position should be a neighborhood of this data instance. And then if the vector value is 0 at one position, and that means the neighborhood corresponding to that position is not the neighborhood of this data instance X. So the phi vector can be constructed in this way. And so as a result, the C function value can be calculated as the inner product of these two vectors. So the X vector and the Y vector, and we multiply them together. That will give us the number of common neighborhoods. So as a result, the NCS can be used in kernel methods. So the C function is a kernel function, so it can be used in kernel methods. So the kernel methods, we know that kernel methods are a class of machine learning algorithms. And the best known member of this class is the support vector machine. So the support vector machine was a popular machine learning algorithms in the early 20th centuries. But at the moment, it is not as popular as the deep learning algorithms, but it has been quite a popular one in those times. And we know that for many machine learning algorithms, including the deep neural network, the raw data has to be explicitly transformed into feature vectors via a feature map. And the power of deep learning is the ability to learn automatically feature representation of any data instance. And in contrast, the kernel methods do not need to learn these feature vectors explicitly, but instead it uses a kernel. It uses a kernel function, which is actually a similarity function over pairs of data points in the raw representation. So the kernel method also uses the concept of feature vectors, but the feature vectors are implied by the kernel function. So whenever you choose a kernel function, then your feature vector has been chosen. So the choice of the kernel function is very, very important. So this is quite different to the neural network. So neural network is able to learn the feature representation automatically from data. But in the case of kernel methods, you need to find the feature representation through your kernel. But precisely what the features means, so that is a question mark. So the meaning of your feature vectors, so that is a question mark. And usually we don't need to represent the data by the kernel feature vectors explicitly. So kernel methods, you typically use a trick called the kernel trick. So we can conceptually work in the feature space by operating in the original data space. So that is the kernel trick. We work as if we are working in the feature space. We can all we need to do is to work in the original data space. So that is the kernel trick. Okay, and the neighborhood counting similarity is generic. So it is generic. And that is because the NCS is defined using the general notion of neighborhoods. So wherever neighborhood can be defined, NCS can be used. And for the multivariate data sets, the neighborhood can be hypertuples. For sequence data, neighborhoods can be subsequences. For tree data, neighborhoods can be subtrees. And for graph, the neighborhood can be subgraphs or can even be path. I'm going to show you examples for all of these later on. Okay, so let's take a quick recap of the neighborhood counting similarity. So the similarity is quite important in machine learning, and some algorithms is critically dependent on a similarity function. And one example is the nearest neighbor. And another example is the k-means clustering algorithms. So the similarity function plays an important role in many. Hello? Okay, and the data come in various forms, and when a new form of data is to be measured, and is there a principle to follow in devising a new similarity measure? So that is a question. That is a question. And even if you are working on a common form of data, you might want to incorporate some additional constraint in your similarity measure. And is there a general principle to follow? And the neighborhood counting similarity provides the framework for you to consider new forms of data or to consider new constraints in measuring similarity. So this can be done through your choice of neighborhoods. And if you choose different neighborhoods, then you are incorporating different constraints. So the neighborhood counting similarity is a principle, and it is a methodology as well. And so the NCS is generic similarity measure. It is conceptual uniformity in handling all types of data. And it is efficient to calculate when specialized to a specific type of data. At the conceptual level, and that is the case, but if you want to calculate for your data, you need to do so in your specific specialization of the data space and your sigma algebra. So next, I'm going to show you how to calculate the neighborhood counting in multivariate data. So which is the next topic, which is this one, neighborhood counting similarity for multivariate data. So that is what I want to go through. Okay, so the motivation is pretty simple. I wanted to specialize the generic neighborhood counting similarity for multivariate data. That was my real motivation. And another side motivation is I want to do the probability estimation in multivariate data space as well. So that is due to the connection between the neighborhood counting similarity and the probability estimation. So these are the driving force for working on neighborhood counting similarity for multivariate data. Okay, and to be able to use neighborhood counting similarity, and we need to specify the data space and the neighborhood space. And for multivariate data, so the space is defined by a set of attributes. The set of attributes A1, A2, and AN. So that is the set of attributes. And every attribute has a domain. But in this case, I assume that the domain of every attribute is finite. So this will allow allow me to do the calculation. So I have wished to extend this definition by relaxing the finite requirement. So that is that has yet to be completed. So that is currently still an open question. Okay, so that is the set of attributes, and then I define a quantity. I define a quantity like this, J of I, so that I define a quantity for every attribute. So this quantity is defined in this case. So if the attribute is nominal or discrete, then it is the power set of the domain. But if the attribute is ordinal or numerical, then this quantity is defined as the set of intervals definable in the domain. So that is the set of all intervals, distinct intervals that can be defined. As a result, the data space can be formally defined in this way. So that is the product of the domain of every attribute. And every element of this data space is called a simple tuple. So this V should be omega. So that is an error. So I call every element of such a specific space as a simple tuple. So this is simple tuple. And the neighborhood space is defined in this way. So that is the product of the J quantity. So the J of I is defined in this way. And every element of this is called a hypertuple. So the L should be F. So that is an error. And so we have the concept of simple tuple and hypertuple. And the simple tuple can be likened as points in the space, but the hypertuples can be thought of as regions or rectangles in the space. Okay, so that is the data space and neighborhood space. And so this is an estimation of the size of that quantity. Now this is an illustration of the simple tuple and the hypertuple. The simple tuple is pretty simple as well. So every line here is a simple tuple, and then the set of tuples is a simple relation. Now on the top right hand side, so every line is a hypertuple. So you can see that in one hypertuple, each field is not a single value, but instead it is a set rather than an individual value. So that is the difference between a hypertuple and a simple tuple. So in the simple tuple, every value is an individual value, but in a hypertuple, every value is a set rather than an individual. And so this plot, so this graph, so that is an illustration of simple tuples and hypertuple. So the small circles are simple tuples, so they are points in the space. And the dashed rectangles are actually the hypertuples. So each dashed rectangle is a hypertuple. And but these are in this particular case we can have we can draw more rectangles than there are currently on the screen, because we don't want to, if we show up all the possible rectangles or the hypertuples, then you probably cannot see which one is which. Okay, and based on the specification of the data space and the hyper and the neighborhood space, we can formally define neighborhood counting metric in this way. So this metric is defined as the C function. So that is and the C function was defined earlier. And here the data space is quite specific, as we have seen earlier, and the neighborhood is also quite specific as well. So the NCM similarity is the number of all hypertuples in F that cover both T and Y. So this NCM similarity was introduced in this paper. That is the nearest neighbors by neighborhood counting. Okay, now, so the NCM similarity is defined, how to calculate the similarity. So that is the question. And this question is answered in this theorem. So the data space is defined by a set of attributes, either categorical or numerical, and all attributes have finite domains. And we assume the neighborhood space consists of hypertuples. And then the C function can be calculated in this way. So that is the product of this quantity, and this quantity can be calculated in this way. So if the attribute is numerical, then it can be calculated in this way. But if the attribute is categorical, it can be calculated in two cases. If xi is equal yi, then it is this number. Otherwise, it is a different number. So that is how we can calculate the neighborhood counting similarity. Okay, so to illustrate the NCM similarity, we take a look at this one. Now this is the domain of one attribute. So that assuming there is a numerical attribute. So if we want to calculate the Euclidean distance, well, now assuming that we have two values, 1 and 3, and if we want to calculate the Euclidean distance, we need to calculate their differences. We look at this interval, But if we want to calculate the NCM similarity, we don't look at this interval, but instead we look at this interval and this interval. And then we multiply the two intervals together, or the length of the intervals together. So this is one interval from 0 to 1, and then the second interval from 3 to 6. We multiply the two numbers together. That will give us the NCM similarity in this dimension. And then we need to do so for all the dimensions. And then we multiply the resulting NCM number together. That will give us the NCM similarity for a multivariate in the multivariate data space. Now we have a specific example. Now we have the data space, And then the neighborhood space is the rectangles. Now we want to calculate the NCM similarity between T and X and T and Y. And in this case, let's take a look at how to calculate T and X. T and X. And to do so, T and X, to do so, we need to look at this dimension. And in this dimension, we have 1 and we have 2. 2 multiplied by 1, that gives us 2. So in this dimension, we have 2. And in this dimension, we have 1, 2, 3. So we have 3 times 1. We have 3 in this dimension. So the X dimension, we have 2, and Y dimension, we have 3. Then multiply them together, we have 6. And then, so that is the NCM similarity for T and X, which is 6. Then what about the Y? Let's take a look at the T and Y. And T and Y can be calculated in this way. So in the X dimension, so we have, this is 1, and that is 2. So we have, so in this dimension, we have 1 and 1. So X dimension should be 1. And in the Y dimension, we have 1 and 2. And this is 1. So for T and Y, we get 1 and 2. That should give us 2. Yeah. So the C, T, and Y should give us a value of 2. Give us a value of 2. Okay, I must correct one error for T, for C, T, and X. So that should be different. Let me do it again. So in the X dimension, we have 1 here, and we have 1, 2, 3. So 1 times 3, that gives us 3 in the X dimension. And for the Y dimension, that gives us 1, 2, 3, 4. 4 times 1, that gives us 4. So that 3 in this dimension and 4 in this dimension, that should be 12. So C, T, and X should be 12, but C, T, and Y should be 2. So that is the NCM similarity for these data points. Okay, and sorry for that. Now we have shown how to calculate the neighborhood counting similarity for multivariate data. Now the question is, how can we estimate probability through this? So we have seen this example before. Now how can we calculate the probability of T? And so I have shown one theorem to show how to estimate the G probability. So that can be done by calculating the neighborhood counting similarity with all data points in the data sample, in the given data set. So in this case, the given data set includes 5 data points, 3 of this class and 2 of this class. And in order to calculate the similarity, calculate the probability of T, I need to calculate the neighborhood counting similarity between T and this, and again between T and this, and again between T and this, and this, and this. I need to calculate the similarity between T with five data points in the given data set. And I have shown how to calculate neighborhood counting similarity in the previous example. So that can be easily done. So once we have calculated neighborhood counting similarity, and all we need to do is to add those numbers up, that will give us a number. And then that number must be normalized by two quantities, And that will give us the G probability. And the G probability has a linear relationship with the P probability. Once you have the G, then you can easily obtain the P value. So I will leave this one as an exercise. Now, I'm going to, next I'm going to show you an evaluation, which is the tic-tac-toe. So this is one game. I'm pretty sure many of you have played this game. So we have a board consisting of nine squares, and then the two players can put the circle or a cross in any space. And if there are three pieces on the line, then that player should win. So in this case, the player with the circle wins. The circle wins because the three circles are on the same line. So this is the tic-tac-toe game. And as people have collected the tic-tac-toe data. So this data actually shows the winning board. So this data set is available from the University of California, Irvine data repository. So you can get this data set from there. And so this problem, so that is the data set, and then the problem is given any data instance, and we want to tell whether this one is a win, or whether this one is a win, or whether this one is a lose, from one player's perspective. Essentially, that is a classification problem. It is a positive class or negative class. So we can forget about the tic-tac-toe game. We just look at the data. So that is the data sample or the training data. And given any data instance, how to classify the data instance by positive or negative. So let's see how to solve this problem by the contextual probability approach. Now the data set is the sample of the tic-tac-toe, as we have already seen earlier. So all attributes are nominal or categorical and have a domain of three values, except the decision attribute. And the data tuple to be classified are these tuples. So we want to classify these tuples. And how to do so? So if we know the probability and the class probability of each data tuple, then we can simply classify according to their class probability. But how to calculate the class probability? And we can do so through the contextual probability mechanism. So we want to calculate the G probability, but in order to calculate the G probability, I need to calculate the C value for every I need to calculate the C value for every simple tuple X in the data sample. And then once I have calculated the C and the C value, then I can work out the G value quite easily. And it turns out, this is my calculation for T1, which is this one. For T1, for this joint probability, G probability, I have this value, and this value need to be normalized, but I haven't done it, and there's actually no need to do the normalization. And the T1 and negative for this joint G probability, I have this quantity. And for the T2 and the positive, I have this quantity. And for T2 and negative, I have this quantity. And to classify T1 or T2, and all I need to do is to compare these two quantities. Whichever is bigger will be the class. So in this case, and this number is bigger than this one, so T1 will be classified as positive. And for T2, this number, so this number is bigger than this. So T2 will be classified as negative. So that is the contextual probability solution, because the G is equivalent to P in classification. So there's no need to transform the G value into the P value. So we can use the G value to classify directly. So that is the solution. So this is the C values I calculated. And so so look at this one. So this number is the neighborhood counting similarity between T1 and this particular the tuple in the data set. So that is the number. And so I would like you to try this, to practice on this one. Now, evaluation, and so the neighborhood counting similarity for multivariate data has been evaluated using public data set from UCI data repository. These are the data set I used. And I evaluated using nearest neighbor, k-nearest neighbor, the classifier. But I consider different the similarity functions. So I use the C function this will give me one version. I also use the Euclidean distance that gives me another version. So this is the Euclidean based version. This is also the Euclidean based version. But so in this case, I use the distance weighting. There's weighting in it. And this is unweighted k-nearest neighbor classifier based on Euclidean distance. So this one is the k-nearest neighbor classifier and it is weighted, and the similarity metric is the C metric. So 3 versions of the k-nearest neighbor classifier using different similarity metric. And you can see that in this case, the k value has been set to the size of the training data. So that is the k value. And from this table, you can see that the C-based classifier is the best for all data sets, except the iris. You can see that the C version is the significantly better than the other 2 k-nearest neighbor classifiers. So that is quite significant. So that is the average values. So that was my evaluation. So this result is published in this paper, which is nearest neighbors by neighborhood counting. So that is okay. So this this table shows the results corresponding to the different k values. So the previous slide shows the result when k is the maximum, but when you vary the k values, you can still compare the results of the 3 classifiers. So when k is the same, when k is 1, you can see the 3 classifiers, they get pretty much identical result. So as k increases, and so their performance varies quite differently. Okay. So that concludes the 3rd part, which is the neighborhood counting similarity for multivariate data. And so now, before moving to the next topic, I would like to have a pause. I would like to take you through some code where we can apply the neighborhood counting similarity. But I would like to have a short break, for 10 minutes break, before we start to work on the practice. Can we come back at 20 minutes past 11 o'clock, which is my time? And so we are 5 hours apart. So let's take a 10 minutes break.
Hello? Yes, sir.
Hello?
Take the break.
Would that be okay?
Yes, sir, it will be okay.
Okay, let's take a 10-minute break.
All right, sir.
Okay, thank you.
Thank you so much.
Okay, so I'm going to. Okay, I wonder if any of you have experience using the Google Colab.
Yes, sir.
Okay, so you do have experience using the Python on Google Colab. Okay, that's good. Okay. Okay, see you again in 10 minutes time.
All right, sir. Thank you.
To Google Colab. So I wonder how you can access the same Jupyter notebook. I wonder if I can simply send the link to you and then you can access it from your computer.
Yes, sir, you can send this link to the chat, so we will easily get this.
Classification. So the first one, the first practice, we will plot the decision boundaries for each class using the default distance metric. And we can just run through the cells. So the first line, we run the first line. Okay, so this one is done. And then run the next cell. So in this cell, let's take a look at what it is, and then we will try to understand every line of it. Okay, after running that cell, we will see those plots. And here you can see the class boundaries using different versions of the nearest neighbor classifier. And have you tried to run from your side? Okay, I want to see. Okay, are you able to run the notebook?
Yes.
Okay, that's great. That's great. Shall we go through the code? So my plan is to go through the code, but I just wonder, so what experience you have with Jupyter, with the Python language? So that is the difficulty of having online workshop. So it is difficult to know every one of you. And as a result, I will just go through the Python code. I will explain every part of it. Okay. Okay, the first few lines. So the first few lines would be there to import the necessary libraries. So this is the NumPy. That is for the data processing, for plotting, and for the sklearn. That is the machine learning library. From this library, we import the neighbors. That is the nearest neighbor classifier, and we also import the data sets from the sklearn library. And we set the number of neighbors to 15. First of all, we need to import the data. We use the sklearn data set, and then we load the iris data. So that is a summary of the iris data. Here you can see that there are 3 classes, and there are 50 samples per class. And in total, there are 150 samples. And the dimensionality is 4. So this is a classical the machine learning data set. And in this case, because so this notebook is to visualize the decision boundary. So we use only 2 features. Only 2 features, because we want to visualize using the data's feature. And there are 4 features altogether. but we cannot visualize the 4-dimensional space. So we choose the first 2 features. So we create the X array from the iris data using all rows, but only the first two column. That is the first 2 column, but all rows. So that is for the X part. In the sklearn or in machine learning, typically we need to separate the X part and the Y part. So in this case, the X part, so that is a matrix, that is a 2-dimensional matrix as a result. And then the matrix contains 150 rows, and every row should have 2 columns. Okay, and the Y part that stores the class label and then the X plus Y together, that is the training data set. Okay, and here that sets a parameter. So this is for visualization purpose. So here we create two lists, because we want to visualize the class boundary, and different classes should be colored differently. So we specify the different colors as a list: orange color, the scene color, and cornflower blue color, and so on. We have 2 lists, and these will be used later on. So one list is for the given data set, and the other list is for the generated data. Okay, now coming to this part. Here we have a loop. We have a for loop, but then this loop only has 2 values for weights in this set. So the weights will take on either uniform or distance. The k-nearest neighbor classifier has 2 versions, and one version is, so when k-nearest neighbors are selected, and then the class probability will be calculated. And now whether we should take every data instance in that neighborhood as equal or not. So we can give every neighbor equal weight. So that is the uniform. Option. But alternatively, the neighbors can be distance weighted. So this means that the closer a neighbor is to the X, then this neighbor should have higher weight. So that is the distance option. And so essentially we are using different versions of the nearest neighbor to run through. Okay, then coming to this part. So we create an instance of the nearest neighbor classifier and feed the data. So here you can see that we use the neighbors. So that is a class. And then we create an instance of this class. So the k-nearest neighbors classifier. So that is one class. and we create an instance of this class, but then we specify some values to this class. That is the number of neighbors, and then the weight, whether we are going to weight the neighbors or not. Then we have an instance of this class. So once we have created an instance of the classifier, then we need to fit this classifier to the given data set. As I mentioned earlier, the data set consists of two parts. One is the X and one is the Y, which is the class label. And then we use the fit method to fit the instance to this data set. And although we call the fit, but actually there isn't very much to be done in the case of k nearest neighbors, because the k nearest neighbor is a lazy classification in the sense that it doesn't need to build a model. It simply uses all the training data instances as the model. So it doesn't do very much. So this is quite different to, for example, the neural network classifier. So in the case of the neural network classifier, the fitting method will train the neural network on your data set, and then the weights of the neural network will be determined during the training. But in the case of the k nearest neighbor, there isn't a lot to be done during the fit process. But anyway, that is the fit. Now moving on to the next few lines. And so that is the plotting part. And here we need to, so we have the X, and the X array consists of two columns. We need to know the mean and the max for each column. And here you can see that this is for this is the mean and max for column 0, which is the first one. So the mean is the actual minimum value of the first column minus 1. So that is taken as the X mean. And the X max is the first column, the max value of the first column, and then plus 1. So similarly for the second column, we do the same, but we label these mean and max as Y mean and Y max. That is the second column. And then, so this line, and the mesh grid. So it uses the NumPy, that is the NumPy. It uses NumPy mesh grid to create a grid because we want to visualize the decision boundary, and then so that means that we need to generate some data that covers the visual space. So we need to generate some data that covers the visible space, and then we classify all the data points, all the artificially generated data points using the k-nearest neighbor classifier. And then we need to color that point by a given color. So that is the logic behind it. And then we use this function. So that is the NP mesh grid. It is called the return coordinate matrices from coordinate vectors. So we have two vectors. So this we generate one vector in this way. You can see this is the x direction vector is generated in this way by using the NP A range method. So that is the mean value, that is the max value, and that is the interval. So we generate so many data points on the x dimension. And then for the y dimension, we need to generate a sequence of y values from the y mean to y max with an interval of h. So we generate a lot of data. And then once we have generated all of these data, we need to mix them up. We need to take one value from the x list and then combine it with all values in the y list. And then we move on from the x list to get the next value. And then we combine this new x value with all the y values. So that is how we generate the artificial data. So conceptually, that is how we do it. But in Python programming, we need to do so in this way. We need to use the mesh grid to generate the coordinate matrices from the coordinate, the vectors. Okay. And if you want to see what you actually get from the x and y's, then you can do it this way. You can do it this way. And what I usually do is and because there is a loop here, I'm not sure if I can have a break. Whether I can debug in here. Okay, but then anyway, this is the secondary. This is the secondary. So in my PyCharm, I set a breakpoint. I can see the actual XX and the actual YY. That will help you to understand it. But anyway, XX is a matrix, and the YY is also a matrix. And then the corresponding elements in XX and YY, so they become the coordinates, the coordinates of the space, and then they also form, and that coordinate also forms the artificial data. So that is XX and YY. And here, and then we call after that, we call the classifier, which is the k-nearest classifier instance. And then we use the predict method to predict values for the artificial data. Then the artificial data are now contained in XX and YY. but they are presented in two separate matrices. We need to combine them. So the combination is done in this way. And through the ravel, so X ravel, that means we need to arrange the elements in the matrix row by row, one row after another. Effectively, we turn the matrix into a huge vector. We have two vectors, and now we need to pair the two vectors into the artificial data. So this is done by using the NPC function. So this is part of the NumPy library. So after this, essentially we have created an artificial data, and each data instance consists of two values, and these two values are actually created in this way. And then we call this classifier instance to predict on those artificial data. And then this Z will contain that should be a vector of the predicted values. So the values will be either 0, 1, or 2. They correspond to the three different class labels. Because in this data set, the iris data, we know that there are, look at this one. There are 3 classes. And so the Z will be, look at this one, Z is, and so that is, so Z becomes, okay, so Z, that is already reshaped. Here, Z, this Z should be just a list of values, or that is one dimensional vector, or just a vector. But here we reshape the Z to become the of the same shape as the XX. And so we have the XX, and we have the YY, and we have the Z. So they all have the same shape in the sense that they all have the same number of rows and the number of columns. And here we use, we call this, so we call this method to create a figure on the screen, which is here. And then the actual content of this figure is generated in this way. So the P color mesh is called, and the parameters are, here we have 3 matrices. We have 3 matrices. So the and the X, so the X that provides the X coordinate for all the points in this space. Because in this space we have many points, 1, 2, 3, 4, 5. And then these, every point in the space should have the x coordinates. Okay, so the x coordinate of all the points in this space is stored here in the x-axis. And all the points in the space should have the y part in their coordinates as well. And the y coordinates of all the points are stored in the y. Okay, and then all points in this space should have a class value. So every point in this space should have a class value. And then the class value is stored in the Z matrix. That is a two-dimensional array. That is 220 and 280 by 80. So that is the matrix. So we have three matrices, and then that is the color map. The color map. So the actual map of a point is based on the value in the Z. And as a result, we will get this one. But here we also want to plot the training points that are contained in the iris dataset. And here we plot all the artificial generated data. But here we plot all the training points in the given data set. So that is how we did it. And look at this. And we scatter this one. We use the scatter, and then the X, the first column, and then the second column, and then we simply scatter those here. And then that is the value of each. That is the value of each data points. These little circles, and then they should be colored, and their color map is stored in the C map bold. So this means these data points will be displayed in the corresponding color depending on its class label. And as a result, we will see these. Look at this one. They actually have different colors, but we can't see them very clearly. But if you take a closer look, then you can find different colors. Okay, so that is the red, that is the dark, and there's also that Syrian color, the Syrian color. Okay, so that is and then you need to plot the axes as well. You can see for the x and y's, you need to provide their, and so these values must be plotted as well. That will help you to understand it. So that is done by this, and then we print the title for this figure, and then we at the end, after the 2 cycle, we need to make them visible. So that should be done explicitly. Because we have a loop here, So this means we run this block of code twice with different weights, uniform or distance. And as a result, we have created two figures. One is based on uniform, the other one is based on weighted. So there are some differences, but not a huge amount of difference. Okay, so that is the visualization. Now, so as an exercise, so I would like you to replace the default distance metric by the NCM similarity. So for this one, I would like you to practice, but I don't know whether whether everybody have some experience writing Python program. And in the k-nearest neighbor classifier, so we haven't actually specified a distance metric. So that, as a result, the default distance metric will be used. And by default, that should be the Euclidean distance, or Minkowski. I think it is the Minkowski distance. So they are quite related. So that is the default one. And if you want to use your own distance metric, you can define one, and then you can specify your own distance metric. So it is quite clear. So we are not going to do this during the online time, but I would like you to practice in your own time. So I will give you the implementation of the NCM, and I would like you to plot the decision boundary of the k-nearest neighbor classifier using the NCM distance metric. Okay, so that is the exercise, but I would like you to do this in your own time rather than in the online time while we are connected. Okay, so this is one. And there should be another one. I'm going to okay. Would you prefer to run the notebook on your own Jupyter notebook, or you want to run it on Google Colab? At the moment, I'm running on Google Colab. Okay, that's fine. Let's do it again for the next one. So this is the first practice. We have 4 practices altogether. Let's move on to the next one. So I'm going to upload the next one. Okay, can you see it clearly now?
Yes, yes.
Okay. Okay, so this one is about the classifying iris flowers. So this is about the plant classification based on some features of the plants. And so the iris data set is a popular, is a classical data set. So we have already seen it in the previous practical, but in this one, let me see how to. Okay, let's do it this way. Okay, so what we want to do in this practice is like this. So we will explore the world of plant classification by using Markov models k-nearest neighbors algorithms support vector machines and other common classifiers to classify iris flowers. So this project will use a dataset from the UCI machine learning repository, which has 150 records with 4 features each. So that is the expected learning learning outcome. We will learn how to import data from the UCI repository. So in the previous example, previous practice, so we use the sklearn dataset, the class. We didn't import the data from the UCI data repository, but in this practice, we import data from a different place. And we build and train classification algorithms and build and train classification algorithms. And then we compare and contrast the classification algorithms. Okay, so that is the problem description, and then that is the learning outcomes. Now the first step of this one is to let me. So the first step is to import the data set. So the following code cell will import necessary libraries and import data set from the UCI repository as pandas data frame. Okay, so so as is common, we need to import the libraries. So in this case, we need the system library, the sklearn library, and then the NumPy library, but we rename it as NP, and we need the pandas library, but we rename it as PD. And then here we need to print out the version numbers, Okay. So that is we need to run it. Let's run. Okay, that is done. And here you can see, so these are the current the versions. So this means on Google Lab, it is Python 3.69. Okay, and the NumPy version is 1.18. And that is this sklearn and pandas. And I suppose that should be the latest versions of these libraries. I suppose the Google Code Lab should have the up-to-date libraries available there. The next point is the next cell is to import data. Now let's take a look at this one. So in this case, we import the data directly from the UCI repository. And all you need to do is to find out the URL for the data. Okay, and then you need to give columns the meaningful names. So these are the column names. But if you want to import directly from the UCI repository, you need to do so. But if you use the built-in dataset in sklearn, you don't need to do that. All of these are already stored in their objects. Okay, and so that is the names of the columns, and then you need to use the read CSV of the pandas library. And look at this one in the UCI repository, and so you can find the data, the iris data, for example, but you can also find other data sets. So they have the extension name dot data, but they are actually comma separated. They are comma separated. So they are textual files. So as a result, you can read those data by using the read CSV method of the pandas library. So you can do it this way. And as a result, you can see the actual data. Let's run this. Let's import it. That's done. That is done. And then let's move on to this cell. So in this cell, we want to inspect the first row of the data, the first row. Because the data is the pandas data frame. And if you want to access the first row, you have to do it this way. You need to use the iloc, that is iLocation. And then you specify the index of the row that you want to access. And so let's run it. And then you can see that that is the first row, but the first row are labeled by the names, So for the first row is like this. For the sepal length, it is 5.1. For the sepal width, 3.5. Petal length and petal width. These are the values for these attributes. And the class label is iris setosa. Iris setosa. So that is the first row. And if you want to change the name here, for example, change the name, and then if you repeat it, then this label will be different. Let's read the data again. Let's run this one again. And here you can see the label of the first value is length, just called length. It is not the sepal length any longer. That is because you have already changed it. Let's restore this one, sepal length. Okay, so that is only the first row. Let's look at all the data. We print all the data on the screen. And here you can see there are 150 records altogether, indexed from 0 to 149. So that is the row index. And these are the data columns. So every row is a data instance, and the last one being the class attribute. Now moving to the next step, the pre-processing the data set. And at the moment, the data set is stored in the pandas data frame, but this is not a data format, and that is typically used in sklearn. And the sklearn and it works on array data type rather than data frame, rather than pandas data frame, because the pandas data frame stores a lot of additional information or descriptive information, and the array data type stores only numbers. And without the metadata, and an array is just an array of numbers. It is not so meaningful. So that if you want to find out the meaning, you really need to use the metadata. And the metadata is not stored in arrays, but stored in pandas data frames. So the data is not in a usable form. As a result, we will need to process it before using it to train our algorithm. Let's take a look at this one. So here we need to separate the class attribute, and then we only print the first 5 class labels. And here you can see the first 5 labels are all setosa. And so this doesn't do very much. It simply store the data object in a different variable. Now let's take a look at this one, this line. Okay, looks. Okay, let's look at, start to familiarize ourselves with the data set so we can pick the most suitable algorithm. So we need to have a better understanding of the data set. So to know the data set, we need to have a better description of the data set. So we can use the data frame. Look at this one. DF is data frame type. We can use describe method. So it generates descriptive statistics. Then let's run it. And then that is what we get. So this means that it provides descriptive information for every column. You can see for the sepal length column, it tells us there are 150 rows. The mean of this row is the standard deviation, the mean, and then the 25%, the average of the 25%, and the average of the 50%, and so on. That is the max value. And so it repeats for all the columns. So that is what the describe method does. It gives you some description. So for these ones, 25%, the 50%. So the describe method will rank order the columns value, and then so the first 25% has an average of this value, and the first 50% in that rank order and average to this value, and then the first 75% of the rows in that rank give you this average value, and so on. That is the max value of this column. Okay, and we can print if we want. So that is what we see. And I think we can get rid of this. We have already print. That is the same as this one. Let's get rid of this. Okay, let's move on to this one. And here we need to, let's take a look at this. In this cell, and here we need to separate the training and testing data. We need to put them in 2 separate matrices. So this is quite And so this is quite so this is quite typical for the machine learning. So we need to separate the data set into the X part and the Y part. X part consists of all the independent the variable values or independent attribute values, and the Y stores the dependent, or we call it the class attribute. And the X, that is the independent, the Y is the dependent. But here we need to obtain the X part, but at the same time we do the conversion. And here you can see that we need to drop the class column, drop the class, drop this column. And then we perform this one in that axis, So as a result, the class column is dropped. And then we need to convert it into the NumPy array, which is the NP array. We need to do so. So that will convert from the pandas data frame to NP array. And then for this one, for the next line, we only keep the class column. Keep the class column. So that will select one column from the data frame, and then we convert it into NumPy array that give us the Y. And here, that is the seed value. So this is mainly for reproducibility. And if you don't set the seed, then every time you run the algorithm, you will get a different result. But if you want to get the same result every time you run it, you have to give it a seed. And then we call this one, we call the train test split. So that is a method in the model selection class. The model selection class is one class in the sklearn library. So the model selection class has a method called the train test split. So this method will split the training data, including the X and Y, to split the training data according to some ratio. Here you can see that is the ratio. So this means that 20% of the data in the training data set will be used as the test set, as the test data, and the remaining would be used for training. And then train test split is done randomly, but with a seed of using a given seed. So it is not completely. So it is random. It is random according to the seed value. Okay, and as a result, we get 4 separate arrays. So this is the training part. So this is the X train and X test. So this means that the X has been split into 2 parts. One is for training, one is for testing. And Y is also split into 2 parts, one for training, one for testing. Okay, and then this one is for a different purpose. We can ignore this one. So this is what I added last night. But I think for today's purpose, we don't need it because this one is needed for the NCM similarity. Okay, moving on to section 3, step 3. So training and testing the classification algorithms. So now that we have pre-processed the data and build our training and testing data sets, we can start to deploy different classification algorithms. It is relatively easy to test multiple models. As a result, we will compare and contrast the performance of 10 different algorithms. Here we have 10 different algorithms from the SK library. Now let's take a closer look at these algorithms. Okay, so from the SK library and then the neighbors class, we can import this one. Import this. That is a class. That is a class. And from the neural network, we import the NLP classifier. So that is another class. From the Gaussian process, we import this class. And the Gaussian process kernels, RBF, decision tree, and these are all imported. So all of these classes. And the metrics, and the accuracy score. Okay. Here we introduce a variable to store our choice of scoring. Because for your experiment, you can record the accuracy, but you can record other things as well. And here we define models to train. So we create a list like this, create a list. So that includes the various, the model names, including nearest neighbors and so on. And then we create another list of objects. So in this case, the classifiers will store an instance of the different classes. And here you can see so the first one is the k-nearest neighbor classifier. That is a class. And then we give a value to this parameter. If we don't give a value, then the default one will be used. So here we call this class to create an instance, and that instance will be part of this list. And similarly, for the Gaussian process classifier, we create an instance of this class with these parameters, and then this instance will become part of this list. Okay, and we need to do so for all of these. So that is the classifier stores a list of classifier instances. And then here we use the zip function. So that is the Python function. And this function is able to combine the two lists to create a dictionary. And then as a result, and then so one entry will become the name of the classifier, and followed by colon, and then the instance of the classifier. So that is the result. That is what the zip does. And then we create an empty list and then the results will be pushed into this list, and so on. Okay, then coming to the loop, the loop. So within this loop, we take one element from this model, from this models list. Look at this one. The models is created in this way. So that creates a list, and every list is a pair consisting of one name and the corresponding instance. Okay, so for one, hello? Hello? Okay, and for one pair of elements in models list, then we run this block of code. So the first line means we use the model selection object, and then we use the k-fold. We use the k-fold. So that is a class. The k-fold is a class, and here we specify some parameters that includes the number of splits, random state seed. So this means that will create a k-fold cross-validation instance, and this instance is stored in this variable. So that is a cross-validation instance, and then and then we call the cross-val score function within the model selection class. And here we need to specify which model we are going to run, and the model is obtained here. And then we need to specify the training X and the training Y, and then we provide the cross-validation instance. The cross-validation equals this one. So the system should be able to find all the necessary parameters in this instance. And then the scoring method. So the scoring method that has been specified earlier on. Okay, and then the every call of this method will produce the CV result, and the CV result is appended to the list. And initially this list is empty, but as we go along, all the CV results will be stored in this list. Okay, and then the names would be appended to this list as well. So you can see the model has been used, results generated and put into the list, and the corresponding name would be stored in names list as well. And then a message is created and print out. Okay, and interestingly, once we have, okay, so that is the cross-validation result. And after that, we need to fit the model. We need to fit the model to the training and the test data. So you can see the model is used twice. It is used once here, and it is used the second time here. So in this use, the model is called on some part of the X and Y, and then tested on the remaining part. So that is mainly for the for evaluation purpose. So the method is called the cross-validation. So the cross-validation is usually used to select optimal hyperparameters. So once the hyperparameters are selected and fixed, and you can, once the hyperparameters are selected, and then you can fix those hyperparameters, and then you can call the model once again to fit and to create an optimal model. But in this case, we didn't do the hyperparameter optimization. So we simply called the model again to fit the model to the whole of the training data. And then we generate the predictions, on the test data set. And then the accuracy, the test accuracy, the predictions, the actual test and the predictions will be displayed side by side and then printed. And afterwards, we call the classification report, and that is based on the test and the actual, the true labels and the predicted labels. So this is mainly to create some precision analysis. Okay, so that is this cell. Let's run it. It is running. Okay, let me see why it is still red. Oh, it seems to me there are some errors. Model selection is not defined. Model selection. Oh, that is because we haven't actually run this. We need to run this one first before we run this. That should be okay now. Oh. Let's run this. Why? That should be okay. Model selection is here. And then okay. It is running. Okay, it is running properly now. Let's take a look at the result from the very beginning. Okay. Look at the first one. The first part is the nearest neighbors. Nearest neighbors dot. So that should be, let me see, that should be the cross-validation result. And that is the nearest neighbors, the model print message. Yeah, so that is the model and cross-validation mean standard deviation. Yeah, that's right. Okay, so this means, and that is the nearest neighbors. And then that is the cross-validation result mean. And this one is the cross-validation standard deviation. Okay, so that is the first message. And then the second message is the test accuracy score. And then this is from the second print. We have the test and then the name, that is the nearest neighbor. And that is the accuracy score. So that is 100, that is 1.0. That means it is 100%. So the and the tests, all the tests data are correctly predicted. So that is correct. And then there is another one. This is the to print a new line and then the print classification report. Okay, so this part comes from the classification report. So we have the true labels and the predicted labels. So, and then it generates the precision recall F1 MEM score and support. So this means, so IRIS, this class, the precision is 100%, the recall is 100%, and the F1 score. And so this means the support means there are 13 data instances which are correctly classified as IRIS Setosa, and the 16 instances are correctly predicted. And these are different measures of your evaluation. And then we repeat this for the second classifier, the Gaussian process. So that is the cross-validation, average or mean, that is the standard deviation, and so on. So that is the result. Looking through this set. So the nearest neighbor gave us 0.946. The Gaussian process is 0.95, that is better. Decision tree is only 0.93. And the random forest is 91. Neural net is 94. Neural net. ADA boost is 97. That seems to be the best. And naive Bayes, this is 94. Oh, SVM is the best, 98. And SVM again, 95, 97. Okay. So you see the SVM, oh, this one is quite bad. SVM, when the kernel function is sigmoid function, look at this. So this means that for the support vacuum machine, the different kernel functions makes a huge difference. And if you choose the wrong kernel function, then you will end up with poor performance. And the support vacuum machine is very much dependent on the kernel function. And if you choose the right kernel function, it gives you very, very good result. 9.8, that is the best. So there are various kernel functions that you can choose from. Although this one is called linear, because the kernel function is non-linear by definition, but the linear means that, and then you still need to use another function to transform your linear function into a kernel function. So that is this one. Okay, I think probably there's no time for question. I want to quickly move. Hello.
Yes, hello. Hui.
Hello, and then I have one final Jupyter notebook to go through. Okay, so this will take about 10 minutes, and then we will stop there. Will that be okay?
Or we can continue from here tomorrow.
Tomorrow.
Yeah.
Okay, you think it is better to do it that way?
Yeah.
Yeah, that is okay. That is okay for me. Okay, okay, in this case, I will stop sharing, and then we can go back so that we can see everybody. How can I stop share? Okay. Okay, so I think, so the Professor Sadiq,
Yes.
is that the, so we stop here for today. Okay, then that's it all for today. And thank you very much for your attention.
Thanks for you to spare a lot of time for us.
Okay, it is a great pleasure. It is a great pleasure.
Thank you.
Okay, then see you again tomorrow.
Yes, sure.
Yeah. So it is still it is noon time here in my place. It is probably already dark in your place.
Yes.
Okay. Okay, that's fine. Okay, thank you. See you tomorrow.
Thank you.
Yeah, thank you, doctor. I think it's a very good lecture. We people have learned a lot about machine learning as well as some probabilistic as well. So I think I'm very much glad to attend this lecture.
Okay, thank you. Thank you. I'm glad to hear that. Thank you.
For attending the workshop. So inshallah, we will continue the session tomorrow at 2 o'clock. All the participants who are attending this online and physically are requested to join 15 minutes before, so that we can start the session exactly at 2 o'clock.
Okay, see you tomorrow.
See you. Bye-bye.
Okay, bye-bye.